Okay, I'm going to start by looking at a switchgear. So in this online drawing, I have a switchgear model with circuit breakers, the main circuit breaker, and some feeder breakers. When we perform arc flash hazard analysis, there may be cases where we have to consider what the hazard level might be at different locations within the equipment. For example, if you have this main breaker, if you get an arc on the line side of the main breaker, then you would have to rely on an upstream trip device. In this case, it's going to be this relay upstream to the switchgear that will need to trip and protect the worker. If you have an arc flash on the load side of the circuit breaker or on this main bus, then this main breaker tripping is going to interrupt the fault. If you're working on one of these cabinets for circuit breakers, then if you get an arc flash, most likely your arc is going to strike on the line side of these feeder breakers. So the hazard level is going to be pretty much the same as the bus hazard level. And next, if you have an arc on the load side of the feeder breaker, say you're working on one of the feeders, then most likely this circuit breaker will trip and protect you. So these are the various conditions, and in most distribution systems, the circuit breakers are coordinated for time intervals, and therefore the speed of the circuit breaker in tripping is what really determines the magnitude of the arc flash that you might be exposed to. So in EasyPower, we have the options of controlling where do you want the analysis based on. And now we'll take a look at the short circuit options. Click on SC options and go to arc flash tab. So on the right side, we have worst case arc hazards. And the first field that we want to make sure we have correct is the output selection. So I'm going to define what these different options mean. Right now we have the choice including main. So including main means the program is going to assume when you fault this bus, okay, let's say I faulted this bus, the program assumes that this circuit breaker will trip and interrupt the fault. So this analysis is applicable not for the incoming line on the main breaker. It is only for load side arc flash, and therefore it's important to check what your options are when you're doing the analysis. So if somebody needs to work on the line side, most likely you're going to have higher energies. So including main means the circuit breaker, the main circuit breaker is going to be the trip device for interrupting the fault. Next option is excluding main. Okay, so when I clicked on OK, you see this energy changed from 15 calories to 93 calories. And the reason for that is now for this fault, we have to rely on this relay and breaker tripping. So the meaning of excluding main is that when you fault a bus, the main breaker or main device that is upstream to this, immediately upstream to this bus, is not the primary trip device. So if you have to work on the incomer, the line side of the main breaker, then you have to choose excluding main condition. Now in general, by default, whenever you create a new one-line drawing in EasyPower, The default is we set it to excluding mean because that is believed to be the most conservative analysis. Now, there may be cases where you may want to have multiple labels. One for working on the incomer and the other one for working on the rest of the system. In that case, you can choose both, that is including and excluding main. So when I click OK, I get two results. So the higher results is for the hazard that is applicable for working on the line side of the main breaker. The lower hazard is for working on the rest of the system on the switchgear. Next, we have a fourth option, and it's called detailed. So when I choose detailed, I get different results here. The first one that I get is the hazard level on the load side of this bus. So if you're trying to work on the main bus or any of these compartments for feeder breakers, then you would have this including main result. This is the excluding main result, or the same thing as working on the incomer or the main breaker. Next, we also give out results for each of the feeder breakers. Now, one thing to keep in mind is, we need to make sure we're not confused with this. This is not for working on these feeder breakers. This is the result for working on the feeder, assuming your feeder breaker is going to trip. So if you're going to work on the feeder breaker, keep in mind you can get an arc on the line side of this breaker, and therefore this result will not be useful for you. You should be prepared to experience this much of hazard level, 15 calories. So just to repeat this, the feeder results that we provide when you have the detailed option is for working on the load side of these feeder breakers, not on the breaker or not on the line side. Now we will take a look at our flash hazard report. I'm going to press F8 key on the keyboard, or I can choose Window and choose Arrange for Arc Flash. So when I do that, the one line gets placed above the arc flash hazard report, and this gives me a good view so that I can investigate what's going on. Let's go through these options one more time. When I have including main, I get just one line of results. Now I'm going to switch it over to excluding main. I still get one line of results, slightly higher values because you're working on the incomer. Then I choose both including and excluding main. I get two rows of results for the same bus. The first row is always for the incoming. That is always for the including main condition, or you're working on the bus and you're protected by the main breaker. The second row is for excluding main condition, or you're working on the incomer. Next, I'm going to switch it over to detailed. So that's the detailed view. So you see all these different rows in the arc flash hazard report. Again, the order is as follows. The first row is for including main condition, meaning you are protected by the main breaker. The second row is for incomer, or you assume that the main breaker is not going to protect you, you have to rely on an upstream trip device. Then we list the feeder breakers, and this is for working on the load side of the feeder breakers. Now in the arc flash hazard report, you can expand the working distances. So when you expand the working distances, you can see different working distances as specified in the arc flash hazard options. Now if you want just one working distance, all you have to do is go to the arc flash hazard options and delete the other options. So I'm going to do that. Click on SC options. In this spreadsheet, you'll see by default we have 3 working distances. So if you want to reduce the working distance to just 18 inches, for example, all you have to do is delete them. So what I did here is went to these cells in this spreadsheet and deleted what I didn't need. So I'll just go for this for now. I click OK. So even if I try to expand the plus sign, I see that I get only one working distance. Okay, so if you have to change the working distance to a less smaller value or larger value, you can just type in a different number here. For example, let's say you're working on switch gears. For switch gears, if you want to use a 24-inch standard, then you can just do that. And that will show on your report as well as your analysis. So when you enter the working distance, make sure you choose the appropriate voltage range. The next field that we're going to look at in the short circuit options is the standard. These are different calculation methods. By default, we set it to IEEE 1584. That's the most widely used. And so far, among the published standards, that is the one that has the most amount of test data and a more rigorous statistical analysis. Apart from the 1584, we also have some other methods that is based on Annex D5 and D6 in the NFPA 70E standard. And these are also known as the Doughty equations. So I'm going to set it back to 1584 standard. Now, apart from these 2 published equations, we also have V7 and V6 enhanced equations. These are primarily proprietary equations developed by EasyPower, and they're based on the same set of data as the IEEE 1584. The 1584 standard talks about taking 2 arc current estimates. So the estimates are based on 100% of arcing current based on the equation and 85% of what the equation gives. And what the program does is to follow the standard, it calculates the incident energy for both of these cases, 100% case and 85% case, and whichever gives the worst case incident energy, that is reported. And when we report the worst case, you'll see on this report at the bottom, some have pink color, some have black. So this is an indication that whenever the 85% arc current has higher energy than the 100%, we show it in pink color. The black color text shows that it's the 100% arcing current that has higher energy. In general, these are the standard percentages, so I would recommend not changing them unless the standard itself changes. Now, apart from taking 100% and 85% of the arcing current, there's also an option of using a bolted fault kiloamp percentage, and I've seen some people using that, and the typical values that have been used are more like 38 to 40% of bolted fault current for arcing current. But again, that's going out of the standard and trying to do your own calculations. Next, we're going to take a look at the max times field. In many cases, what can happen, specifically if you are on the secondary side of any transformer, any distribution transformer, your trip times can be significantly high. That is, a lot higher than 2 seconds. And IEEE 1584 standard, as well as NFPA 70E, the 2012 edition, says that if your calculated trip time is higher than 2 seconds, it's okay for you to assume a 2-second maximum time. And that is based on the assumption that the person working there will move away quickly, and 2 seconds is a reasonable maximum time. So you can set your time limit as you desire, and that is something you'll have to exercise on your own. So right now, if I want to set a 2-second time limit there, I can just type in the number 2 in these fields. So right now we have 3 categories: less than 250 volt category, 250 volts to 1000 volts, and anything greater than 1000 volts. So I said that. So when I do that, my arc flash results are going to change for those buses for which the calculated trip time was higher than 2 seconds. Now you see some values changed out here, and it got limited to 2 seconds there. Okay. So in this example, I'm going to choose excluding main, and see that this breaker is tripping fairly quickly in 0.89. Oh, this is fuse. Let's say you had a slightly larger fuse. Okay. So the calculated trip time for that slightly larger fuse was 2.32. What the program does is it just limits the arc time to 2 seconds. Okay. Next, we're going to talk about a few advanced options. Some of you are probably familiar with the term bus orientation. When the IEEE 1584 committee did some tests back in 2002 or prior to that, the lab had this electrode or conductor configuration such that the conductor was, in a vertical position, and the source was connected towards the top of the conductors, and the arc was facing downwards. Now, one of the properties of arc is that arc tends to move away from the source and come outwards from the conductor. So that is pretty much a physical property of the arc. And later, after the 1584 standard was published, there were some other engineers that pointed out, if you have a horizontal configuration, the arc can come out towards you and much closer to the worker. And in such cases, the incident energy can be significantly higher. And so that was the first, let's say, talk about looking at bus orientation or the orientation of the conductors with respect to how it affects workers and incident energies. Later on, there were other group of engineers that pointed out, if you have conductors that terminate on an insulating barrier, then the barrier tends to hold the arc, and it gives out much more incident energy than what a vertical configuration would give. And based on the testing terminology, we have three different conductor orientations. So if you go into any bus dialog, that is, once you're back in the database edit focus and you go into any bus dialog, if you go to arc flash, you will see this field called orientation. By default, we have it as vertical because the IEEE 1584 standard is for vertical orientation of conductors. The other choices are horizontal and vertical into barrier. So when we do that, what happens is that the incident energy changes based on the multiplier that we specify. So I'm going to do a quick exercise here and compare the two, or compare the three different types of buses. I'm going to make a copy or a duplicate. So I'm going to change the name of these buses. So this one I'm going to call vertical. And when I go to the arc flash tab, this is for vertical orientation. Next one I'm going to call horizontal. And change the orientation to horizontal. And finally, this one I'm going to call V into barrier. So I'm going to set that into vertical into barrier. Okay. So go into short circuit for all these three buses. See the incident energies? Although they are identical, because the orientations are slightly different, we have used a multiplier to calculate the higher incident energy. So now some people have been confused with this configuration or orientation of the bus. For example, if you have a switchgear or an MCC, you might have vertical bus and horizontal bus. Now, one thing to keep in mind is the vertical and horizontal is not so much how it's oriented in space. It's more like how does it relate to the worker standing in front of it? If the conductors are pointing towards the worker, and there is a likelihood that when the arc moves away from the source, the arc will come closer to the person, then that's when you have to choose horizontal. Otherwise, you can just leave it as vertical. And that's something we have explained in our help. So let me show you some pictures here. The bus data, arc flash hazard. So here are some examples. So here in this Switchgear or MCC, I've shown both vertical and horizontal configurations. In the testing sense, these are both vertical, because if you are standing in front and you get arc on one of the conductors, then the arc will try to move away from the source. Now, in this case here, you've got conductors pointing towards the worker. That's when the arc will come closer to the worker. And that is what we classify as horizontal configuration. Now we'll explore a few more options for arc flash hazard. Towards the bottom, you'll see this advanced. Click on that, and you get the advanced arc flash options dialog. The first checkbox is for including the 1584 current limiting fuse calculations. Now, if you have RK1 fuses or Class L fuses, there are separate equations for evaluating arc flash. And when you apply those equations, you do not have to calculate the arcing current or look at the time current curve to calculate the trip time. The current limiting fuse equations automatically give you the incident energy based on just the bolted fault current. So you have the choice of applying that. And keep in mind, this is again meant only for RK1 and Class S fuses. We do not have any equations for other types of fuse classes. So when you check this box, you will get the results for current limiting fuses. So I'm going to check that box and maybe insert a few current limiting fuses here. I'm going to insert a fuse switch. So that's an RK1. So I'll choose a 400 amp fuse. I'm going to short circuit and fault this panel. Okay, right now we've got the breaker tripping faster than the fuse, so let me deactivate the breaker. Okay, so whenever any arc flash analysis is based on the current limiting fuse equations as specified here, you'll notice that the arc current is not calculated at all because the equation calculates the incident energy directly, and you'll also not get the trip time. So anytime you see arc current as being blank, then that's an indication that it may be using the current limiting fuse equation. The next field is for arc flash boundary. Arc flash boundary is defined as that distance at which the incident energy is 1.2 calories per square centimeter. So this is based on the standard NFP itself, so I would advise do not change it unless the standard changes. Next, we have this minimum relay trip time. As per IEEE 1584 standard, what the standard says is if you have a fast-acting relay, then take the minimum time of 0.016. So if I want to follow the standard, what I have to do is make sure that I have 0.016 specified in that minimum relay trip time. Now, anytime you create a new one line, by default we set it to 0.016 seconds. Next, we're going to take a look at this traverse count. I'm going to open up a different sample file here. So I'm going to zoom out a bit. So what we have is pretty much a picture of something like a riser. Let's say we've got different floors in a building, and this is a bus duct going from one floor to another, and you've got tap-offs on every floor. And you need to calculate the arc flash hazard at each of these floors. So I have a very long chain, or daisies chain, of busways. So when I fault all buses, you'll notice that I get results. But I'm not getting results for bus number 15 and 16. And the question is why? So anytime you have very long feeders with lots of tap-offs or buses connected like this, then you can go to short circuit options and advanced tab and look at this traverse count. The meaning of traverse count is the program traverses upstream towards the source when you fault a bus. And by default, we have a maximum traversal of 12 buses. So meaning the program will go up to 12 upstream buses to look for the upstream trip device. And this is done to optimize for speed. Now, in most distribution networks, you probably have things like switchgears feeding panel boards and feeding smaller panels. And most likely you will find the upstream trip device, except for feeders like this example. So what you would want to do for such feeders is increase the count to say 25, whatever your number is required. Click OK. Now I get results here. So anytime you have a long chain, just make sure you have increased the traverse count to adequate number as per your requirements. The next option here on the right side is PPE level, show PPE level. Now, this is more of a recently added feature. In the past, we always used to show the PPE level or the hazard category risk level. And in 2012, after the publication of the 2012 NFPA, we have made that a choice. You can show or hide the PPE level and just show the incident energies as per the detailed calculation requirements. So if you want to show the PPE level, you have to check this box. By default, we keep that unchecked, or we do not show the PPE level. So if you check that box and you want to use the old 0, 1, 2, 3, 4 category systems, then choose this option here for PPE levels, NFPE 70E 130.7C16 table. So that's the NFPE table that we refer to. And click OK. OK. And then you get these category numbers. Now, this other option of PPE level is this 3 category system that is defined in the Annex H3B. I think they have categories that is 1.2, threshold, 12, and 40 calories. So it's slightly different from the previously used 0, 1, 2, 3, 4 categories. So anyway, you have the choice of which table you want to use. The next option, apply LVDC for greater than 1 kV equation. If you look at the NFPE 70E standard in the Annex D8 in the 2012 edition, you'll see the DC arc equations, which is based on a theoretical maximum power transfer theorem. And that one has been suggested for low voltage systems. And so far there are no known published equations for medium or high voltage DC systems. And what we have done is allowed you to extend that equation to greater than 1 kV system, voltages. So I'm going to enter a very small DC system here and show you how DC systems are calculated for our flash. When you model any DC system, it's pretty much like modeling AC equipment. There's not much difference there, except for the type of analysis we do internally. So this is fed by a battery. Okay, so there's my system there. Say about a total arc duration of, let's say, 0.1 second. So I can perform calculations now. If I pull this bus and look at the arc flash results, I get arc flash. Answers there in a very simple DC system, just a battery. If I look at the arc flash hazard report, there we go. Now, if you want to model, let's say, medium voltage systems, say this is at a higher voltage, say 2.5 kilovolts. Okay, it says the buses have been excluded from arc flash calculations. And let's take a look at the advanced option now. So I have to check this box to allow for DC calculations above 1000 volts. Now I get my results. Okay, so by default, that checkbox for medium voltage DC is unchecked. Next, we're going to take a look at open air calculations. For those of you that may be involved with having to work in switchyard or open air buses on transmission lines or distribution lines on the poles, this may be applicable to you. So what I'm going to do is, this feeder is, let's say, feeding to an open air distribution line. Okay. I'm going to enter some data for this overhead line. See, that's half a mile. And AAC size, say 4/0. Say this is the end point, and we've got an open air bus out here. I'm going to set the type to open air. Okay, so since this is open air, the conductors are going to be fairly widely spaced, and most likely the only type of faults, arc faults that you might be getting is line to ground fault while somebody's working on it while it's energized. So when we do arc flash calculations for line to ground faults for open air buses like this, what we can do is make sure that we use the appropriate method. Now, if you look at the previous version of NFPA 70E, that is the 2009 edition, in Annex D, it gives you what the hazard level might be for working on open air systems for medium voltages or high voltages. Okay, so right now, when I fault this bus without setting the options correctly, this is using pretty much IEEE 1584 equations for three-phase faults. So if I want to set it and get a better estimate for the line to ground fault for open air buses, I can go to Advanced and check this box. Okay, apply to open air buses. So when we do that, it will no longer use the IEEE 1584 equations. It will use the Annex D equations, which is mainly used for high voltage systems in open air. And that's how you can do open air calculations. Okay. Now, the equations or the methodology that has been prescribed is meant for line to ground faults. If you want to estimate what kind of energies you might have for line to line or three phase, then you can assume some multipliers. Right now we've just put in some 2.2 and 1.5 as the multipliers, and there is no test data or any calculations principles involved with that. These are just estimates to be conservative. Okay, earlier we talked about controlling the working distance for general option, that is a global option. We can also have individual working distance for specific equipment. For example, if I go to this, any bus dialog and go to Arc Flash Hazard tab, you'll see this choice here, working distance, default from options. So that options is basically looking at the short circuit arc flash option spreadsheet for working distances. Or let's say you want something different, then you would have to choose the user specified and type in your value that is required. Okay. So there are also bus specific options that we can apply for Arc Flash. Earlier we're looking at the global options in the short circuit dialog. If you want specific options for any particular bus, you can set that. So you can set it to including main, excluding main, or both including and excluding main. And the rule is that whenever you have a bus specific option specified, the program will give that a priority over the global option that you have specified. So this takes precedence. Another option that we have for bus specific Arc Flash Hazard data, I'm going to go through these. TCC times. Okay, so TCC times automatically calculated means the program will look upstream from the faulted bus and try to find the upstream trip device that is responsible for tripping. So that's how the arc time is calculated. There are some manufacturers that have some devices that quickly extinguish the arc. For example, the arc fault, which is pretty much an arc chamber, where they have an internal short circuit that reduces the voltage on the bus and therefore extinguishes the arc because the voltage is not adequate to sustain the arc. So if you want to model something like an arc fault and the arc is guaranteed to be, quenched in say 7 or 8 milliseconds, then you can enter that in the bus data dialog. So I would go into this dialog, go to Arc Flash tab, and set user defined times. So I'll just call this arc fault. Okay. And have a time of 0.008 seconds. Now, right now we do not have anything specifically, called arc fault. And so if you want to indicate that you have an arc fault, what you can do is insert a note with a leader, something like this. So you can just put in a symbol like this indicating that, hey, there's an arc bolt out there. Now, when it comes to analysis, we've already entered the arc time in the bus dialog. So go into short circuit, and when you fault the bus, you get very low energies. So if you look at the report, here you'll see that arc time of 0.008 seconds, as you specified in earlier. So let's see what else we have for bus-specific arc flash options. Now, there's one more item I wanted to discuss. We have this third option called Predefined Fixed times. Basically what this does is it accesses the library and gets some fixed time, which is pretty much saying you do not want to look at the upstream trip device. You just want to assume certain times, like instantaneous or short time trip, etc. I would recommend not using this option. This is pretty much a legacy option. Long time back when we just started Arc Flash, there were some users that did not have the ability to look up time current curves because they did not have coordination package. And so this feature was put in there just in case you did not have the coordination package. So this is an assumed trip time. So this may or may not be applicable in your case. So my recommendation is never use this option, predefined fixed times. Okay, I think that's what we have for today. What I'm going to do is try to answer some of the questions that you have. In case I have more questions that I need to answer, I could probably create a log of the questions and answer and have them available to you next time. Question, will there be a recording of this webinar for later viewing? Answer is yes, we are recording this and this will be available. Next question, can you discuss switchboard versus switchgear and how to handle labeling for each? Typically when we talk about switchgears, we assume that all the different components are in separate cubicles or compartments. So the main bus will have its own compartment with that is enclosed by the metal, and each of the circuit breakers will be in separate compartments. And the switch board, on the other hand, is has less compartments. So when you open up the switchboard, you may be exposed to a whole lot of other things within that switchboard. So with your labeling, I think the best approach is to have a certain norm or practice within the company or the industry. And so that it's not just a labeling issue, it's just to make sure that all the workers that are reading the labels correctly understand what kind of practice that you have. In a lot of cases, just to simplify the process, people have avoided having multiple labels on the same switchgear or switchboard, and they just stick with the worst case hazard that was whatever may be the incoming hazard, or using the excluding main condition. That simplifies the approach. Of course, you might be getting higher hazards based on that calculation, but it may also avoid confusion that is created by multiple labels on the same equipment. When it comes to switch gears, if you want to have multiple labels, then what you will need to do is make sure that the workers understand what each of these labels are meant to do. So I would say just have some kind of a practice where there's adequate training so that the workers know what the person doing the analysis is trying to communicate to them through the labels. Next question, can you discuss the differences between trip time, opening time, and arc time in the spreadsheet? Okay, so going back to the spreadsheet for arc/hazard calculations. So what I'm going to do is remove this user define and choose TCC times. Okay, in my spreadsheet, I've got relay trip time. Anytime we have relays as the upstream trip device, what we report in the trip time is the trip time of the relay. So let me show you a TCC plot. R18 is this one. Okay, if we fault a bus, let's say the fault current is exactly at this 1000 amp mark. So I would get a trip time given by this crosshair. Let me zoom in. So at 1000 amps, I would get 0.679. So that would be reported in your arc flash hazard report. Now, let's do a more realistic case. I'm going to select this whole thing down here. And I will remove any relays that are not necessary right now. Okay, when I fault this bus, okay, I just faulted the bus. On the right side, on the TCC window, I can do a right click and choose arcing current, insert arcing current tick mark. So when I do that, notice at the bottom I have this triangle. That is your arcing current, which is going to be slightly less than the bolted fault current. So I can drag it up until it meets your relay curve. So there's my green relay curve, and I can see from the crosshair that I'm approximately 0.625. Okay, so going back, that is going to be my trip time. That's reported in the arc flash hazard report. So when I fault this bus, 0.621 is what the TCC gives you for the relay. Now, the relay passes on the trip signal to the circuit breaker, and the breaker trips. So the breaker trips at additional 3 cycles or 5 cycles, whatever the breaker is rated for. So let's take a look at the data. I'm going to right click and choose DB info. Okay, this one does not have any data, but you see that this is, by default it has a 5 cycle information there. So that 5 cycle corresponds to this 0.083 seconds. So the total arcing time is going to be the relay trip time plus the opening time for the breaker. So this opening time always corresponds to circuit breaker opening time for medium voltages. Now, TCCs or time current curves that are published for low voltage breakers, the breaker opening time, the contact faulting time, is included there in that TCC curve. So that is the maximum clearing time. So when we have low voltage breakers tripping, see the trip time is blank because you do not need to, sorry, I chose the wrong bus. This one has the bus data time. I'm going to disable this so that we have TCC time. Okay, and set this to including main. Okay, so this is a low voltage breaker. BL1 is a low voltage breaker, which is this main breaker. So when this trip, the trip curve includes the breaker opening time. So what we're getting out of this is, let's say I'm going to fault this, right click on this, insert arcing current tick mark, places the triangle, I'm going to zoom in, drag it up. So that is where it meets the top of the curve, and I'm getting 0.33 seconds. So I can close this out. When I fault this bus, I get 0.34 seconds as the clearing time. So we do not need to add additional breaker opening time. That is included in the TCC. So for fuses and low voltage breakers, we do not need to add any opening time. It's only for relays with high voltage breakers that we need the opening time. And this is the total time. This is the sum of trip time and opening time. Arc time is the sum. Okay, next question is known that 85% is higher than 100% will help in choosing setting of OCPD. Sometimes it can get very confusing because when you're trying to change the trip settings, there are times when 85% current gives you higher energy, and there are times when 100% of arcing current gives you higher energy. It all depends on the shape of your trip curve. Okay, were the arc flash calculations for horizontal and horizontal into barrier based on published equations? The answer is this is based on the papers that were published by the original authors of those papers. I think I do not recall all of the details, but one of the authors for horizontal configuration, I think, is probably Sweeting and Stokes, and horizontal into barrier, I think, is Mike Lang and some of his co-workers at Farash Ahmed. But both are published in the IEEE journals. Next question is that fault time for total clear consisting of sensing and breaker opening time. Okay, I think this is something that I just answered previously when we talked about trip times and clearing times. So for relays with high voltage, we have to add the breaker opening time. For fuses and low voltage breakers, we do not need to. Next question was, can you show how to model a large DC motor driven by with a DC drive fed with AC? We're out of time today, so we'll have to do this at a later time. We will be covering DC modeling, so hopefully we should be able to get that covered in the next month or so. Next question, why does some of the arc flash tags go red and some stay black once the analysis is performed? Okay, so that is because of the thresholds. Let me go to short circuit options. We have this column called threshold incident energy. Right now my threshold values are 4. Okay, for low voltage. Let's say I had a threshold of 40. Now let's see what happens when I hit the apply button. Okay, see, it's turned into a dark blue. It's no longer red. So it's the threshold value that you can control in this spreadsheet. I'm going to set it back to 4 again, the original data. Now it's red. Next question. What is auto lock sizing? Okay, auto lock sizing that you may have seen this here, lock auto sizing. That is meant for auto design. So if you have smart design or auto design, then you can avoid resizing of the bus when you perform the sizing calculations. What is the best way to calculate arc flash on a VFD? When we model a VFD, one thing we have to keep in mind is unlike other passive elements like transformers, cables, etc., VFD is a very active element, and it may have its own control mechanism where when it senses a fault, it stops producing an output voltage. And so you'll have to look at the configuration of a VFD itself. Now, let me insert a VFD here on the switchgear. Okay. Okay, I'm going to enter some data. Say this is 150 kVA. Or if you want to do horsepower, you can do that too. Output frequency of 60 Hertz. And I'm going to enter some circuit breaker data here. I'll just go with the molded key circuit breaker. Let's choose generic for now. Okay, next I'm going to insert a motor. Say this is a 100 horsepower motor. I'm going to short circuit. Okay, I have including main for this. I can just fault this. Okay, so there's my arc flash result. Let's take a look. And what it's saying is your upstream trip device is AFD1. Question is why? The reason is in 0.2 seconds your fault current is going to stop. So this is what we have as the default data. So you'll have to look up the data sheets for the VFD or contact the manufacturer for the information. If you were to have a fault, what's the maximum current it might be able to deliver? So that is done as a multiple of the full load amps for the VFD or AFD. And how long will it supply the short circuit current? So those are the two things that we need to enter. And based on that, your results will be calculated. And there's my result. It's using the 0.2. So you'll notice that typically when you model AFDs or VFDs, these have very low short circuit contributions on the load side. Next question, what is the difference between calculate, arc flash using integrated and momentary. We will discuss that at a later time. It takes some time explaining the integrated method, so I plan on doing that maybe in the next presentation on arc flash options. Do you need to date the arc flash label on the time the calculation was made? You can put a date on it. When you print labels, there's an option to show the date for the calculation or when the label was created. There's some question about lighting panels. If you are interested in lighting panels modeling, we can do that later time. I think this was scheduled to be an advanced options for arc flash. Next question, can you comment on how the capstone microturbine source can be modeled? I would say for now, just model it as a motor generator set. And that should be good enough. So let me create a small example here. Let's say on the switchgear, we've got our turbine. So if you have a motor generator set, you can model it as such. So what I would do is model a motor on this side and a generator on the other side. Right now we do not have a way to show a mechanical coupling because this is an electrical one-line drawing. So if this is supplying to the rest of the systems like panels or whatever, then you can use this model. Now another alternative is you can also use a UPS model, which is pretty much internally the same thing. So there's my UPS. So there are different ways. So it all depends on the configuration. What I would suggest is if you have a scheme or some kind of drawing as to how your microturbine is connected, and what we can do is if you can send an email to techsupport@easypower.com, I think we can better model it more accurately based on how the connection is made. Next question, can you please explain the remote current calc setting in AF Advanced option? Okay, so let me go inside things. I'm going to delete this for now and go into short circuit. Okay, remote current calculations. In the past, when we were calculating the remote currents for upstream trip devices, we were pretty much using the equation method. So what the equation method means is, let me show you what it means. Okay, I'm going to set this to excluding main. Okay, so let's take a look at this arc flash hazard report. I faulted this refiner bus, and it's pointing to an upstream trip device of R7. So that's R7. So this is across the transformer. And whenever we take the arcing current for an upstream trip device, we were applying the arc current equations to the upstream remote current. So what we did was we took the remote current and we calculated the voltage fault current through this upstream trip device and calculated the remote current based on that using the IEEE 1584 arc current equations. And later on we added this option here to use a ratio. So when we have the ratio method, let me show that to you. The numbers change slightly. So they're very close to each other, but the numbers change slightly. So when you have a ratio method, what we do is, the difference is that we calculate the voltage fault current here, then we calculate the arc current here. So based on the ratio between voltage fault current and arc current, we apply the same ratio here. So that is the primary difference. Next question, what part of the trip curve can be manipulated to reduce the incident energy? That depends on the trip device. If you have a fuse, you have to replace the fuse itself. If you have relays, then maybe it's got a time dial, maybe it's got a, the short time delay setting or instantaneous setting that you can change. By lowering the pickup, by lowering the trip times, you can change the characteristics of the relay. Next question, did you say that the arc fault is considered 30 to 40% of voltage fault value? Yes, I've seen some people doing that. I would recommend not doing that because the standard says, use the arc current equation. But again, that option is there for those who really have their own information and have done their own testing. Otherwise, avoid using that. Yes, I've seen people use something like 38% to 40%. Next question, what is the best way to handle 120 volt AC panel boards that calculate out to values like 37 calories per square centimeter? Okay, so we're talking about small lighting circuits which are calculating by default high energies and you need to bring it down. I think the best thing to do is maybe go to our website and you can download a paper called Calculating Incident Energies for Less than 250 volt systems. And there we talk about the different methods that you might be able to use. So I guess one of the methods that we have recommended is lowering the time limit, that is the maximum time limit in the short circuit options. Some people have forced it to a low calories and that's fine too. Right now we do not have a whole lot of test data on how much incident energy you might get on small lighting circuits because there's not a whole lot of test information or any calculation procedures that have been prescribed yet. So I would say just go to our website, download that paper on 250 volts and less. Next question. Will we have any regenerative current from the motor through VFD? For when you model AFDs or VFDs, you have the choice of making it regenerative. It's in the dialog, so look at that option there. Soft start modeling, we do not have a separate unit just for soft start. If you want to use AFDs or VFDs, you're welcome to do that. Once the motor has started, if it goes into the bypass mode or direct connection mode, then whenever you've got a fault upstream, it will contribute motor contributions. So you have to look at whether you're doing arc flash with the soft start in circuit or out of circuit. And finally, we have this last question. What is the generic MCCB for? Well, the generic MCCB was mainly placed there for auto design purpose. If you're trying to design new systems and you do not want any manufacturer specific information, then we just wanted an option to give you generic for the sized circuit breaker. Now, if you have any circuit breakers where the nameplate has been, scraped off, or you cannot read it, you don't know what it is, and you think you might be able to get by using generic, you're most welcome to use generic as a standard estimate for that particular circuit breaker for which you have no other information. So that is the last question. Thank you very much. We will be placing this video on the website soon. If you have further questions, please feel free to contact techsupport@easypower.com, and we will be able to answer your questions in detail. Thank you very much, and have a good day.